OpenMP and OPARI and MPI. And so here's some results that show you what's going on with this, and I think there's a question.
Yeah, Phil, question at NCSA.
Hi, I'm just wondering if those results you're showing are just for long-range interactions in MD, and if it's good to still use that even though if you don't have the long range. I'm confused with that.
I think what's going on, I think what's going on here is, now I'll have to, Axel has benchmarks on lamps. But I think that if you don't have any long range, like all-to-all communication, I don't know. I think the benefit will not be as great. I can't say that it won't still pay off at very high core counts. But what you see, what you see happening here. So this is again this comparison where you add the mean execution time to the comparison window that I showed you before. And so what you see here is I've got 3 pairs of results here. Each one of these, the top one is the threaded version, and the lower one. So there's 3 pairs. So this is 4 threads and 4 MPI tasks on 16 cores. Oh, you can kind of see it here. So this is 16 and 4 MPI. So 16 total cores, 4 MPI tasks with 4 threads. 16 cores with 16 MPI tasks and 1 thread. And so there's 3 pairs, one at 16 cores, at 64 cores, and at 1024. And so this is the most expensive part of the code computationally. This is that main pairwise loop through the code. And so you see that the threaded version at the low core counts is a little bit slower, but also this part here, notice that it's only on the threaded part, this .tau application. This is all the part where the threads are doing nothing because it's just you only have this one OpenMP section of the main part. So all the other threads are idle and only one thread is active on those parts. So you take a hit right there, but as you start to go up and the communication starts to dominate here, see here at 1024 cores, this MPI wait any is waiting for the return of that all-to-all. And so when this starts to blow up, then the advantage of, so here's the threaded version, and the threaded version has no wait, no MPI wait any, and here's with just MPI tasks, you got this huge communication for that all-to-all. So if you don't have to do the all-to-all, then I don't think the benefit will be as great. But as you continue to go up, then you may still find some benefit. So there's this trade-off because you're losing a little bit of the computation. You're still hitting the main loop, but you're introducing some serial regions of your code. So that's the trade-off, plus maybe a little bit of overhead for doing the threading. But you really win when communication starts to become the bottleneck. So I think the key here. The key to success was, well, one, he's doing OpenMP in an efficient manner. He's actually assigning the work manually to the threads in an MPI-like manner. And if you have any questions, you can look at that LAMP source and look in the pair styles, and you can see how he's done that. So I think the keys why this hybrid scheme really worked is efficient OpenMP that actually uses a little bit more of a hands-on approach. You have these architectures with significant multi-core capability, 16 cores on Ranger, 12 cores on Kraken. By the way, these results, actually, it may not be quite, it's at least 2 times as fast on Kraken. He's running mainly on Kraken. And so you have these, serious, you can have a lot of flexibility because you can play with the threading and the MPI tasks. And you've got a code that has a computationally heavy region with basically no communication, and then a region where there's a lot of communication but almost no computation. And so you don't need to have all your MPI tasks working on that region where you're doing just the communication. And so this allows you to achieve much better balance between communication and computation at the high core counts, and that's a recipe for success. So I just wanted to show you that, and you may, if you get interested, and to play with some of your own hybrid things, you can use Tau to play with it and see where the time's being spent and in the threads and tasks and so forth. So I think I'm basically out of time, and but I'm happy to take any last questions or to try my best to respond to those offline also.
One at NCSA?
Yeah, and the graph that you just showed, is there any reason to believe that that would continue on the trail that it's going, or would it also take a peak like the blue curve?
Yeah, it will eventually. It's already. You can see there's a little bend in the curve here, but then it kind of bends back up again. Actually, it kind of bends down and then it bends back up. But yeah, it actually. I know that it scales. I know that you get increased performance at one step higher at 2048, but it's not a big jump in performance. So you start to lose some parallel efficiency there. So it will definitely take a hit, and eventually the communication will swamp. Will still swamp you with the all-to-all call. So there's, but you extend your scalability by a factor of 4 by using this hybrid scheme. And there's still more work to be done to maybe eke out some things. We added like single precision. The FFT is what requires the all-to-all, and so you can use single precision there and reduce the amount of the size of the messages that need to be sent across the network, and that seems to help a little bit. And you can try to find more regions where you do threading, but eventually you'd probably have to find ways around this all-to-all to. But this is for a system size of only 90,000 atoms, so that's not a huge system for MD code, and to scale that to 2048 is a pretty good achievement.
Thank you.
Any other questions?